All right. Good morning, everyone. Welcome. Just a couple small logistics things. I did upload the PowerPoints for this week. They're in week 9 Faraday's Law. I just did it. Obviously, web courses was down yesterday. Other things were as well, whatever. So those are there now. Fingers crossed we'll get to start that PowerPoint this class. That's the hope. To give you all a sense of, I mentioned this before, but just to remind you all of what's kind of left, is we're going to finish up, we're going to do Ampere's law today. We're then going to start Faraday's law, all the laws. And then next week, it's very likely Faraday's law is going to be finished up next Tuesday. But then my hope is then to teach you about inductance and AC circuits. Now, inductance and AC circuits will both be fairly just like formula. Pretty straightforward, just kind of use the formulas kind of situation. And so that works out kind of nicely that we end on something that's kind of just straightforward. So anywho, we'll see how much we can get to. That's kind of the big question. We'll definitely be able to do inductance. How much of AC circuits we'll get to do, we'll see. If we don't finish it, it'll roll over after the test. And then after the test, we'll talk about electromagnetic waves. And then that'll be the end. So, there's that. Don't forget that your all's AI assignment is due this Saturday. So that's the assignment where you're engaging with some AI large language model in a way that is not just put the problem, hit enter, and done. It's the way you're actually engaging with it in a way that is productive for learning. And just copy and pasting the problem, you'll learn very, very little that way if you just look at what it did. So engaging with it in a productive way, the assignment's there all that test.
Just double checking.
Mm-hmm.
Last class you mentioned that we could do the AI assignment on any engineering problem.
Yep. That's a good question. The question was, do you have any engineering problem? Yes, I have any problem that requires critical thinking, which will be a physics problem, an engineering problem. Computer science as well, but that's just going to maybe look a little bit different, less mathy, and more coding stuff. But still, I want you to engage with it in a way that is learning, that is not just put the thing in there, have it spit it out, and you copy and paste that wherever you want. That is not a productive, that is a way of using AI, but you're not learning much in that. It is not productive for learning, it is productive for getting a result. Which may or may not be correct. You might not have thought about it. All right. So there's that. Reminder for what we did last class. We talked about so we've been talking about current carrying wires make magnetic fields, and we talked about two types of wires. We talked about an arc of wire, and we have the equation for that. That's mu naught I times theta over 4 pi r. So that's way at the beginning here. So we have an arc of wire. There it is. We learned how to find the direction using right-hand rule 2. And we learned there was a shortcut for an arc of wire / a loop of wire where you curl your fingers in the direction of the current. So that was right-hand rule 2.5. Great. Last class we learned about the equation for the magnetic field due to a straight wire. This straight wire, the equation I gave you, this is the equation on the formula sheet currently, is a finite wire. Finite meaning the two ends, you can actually see where they're at. Now, you can take this and turn it into the equation for an infinite wire or a semi-infinite wire if you know the answers to the next two clicker questions, which are what is theta 1 when it's infinite, what is theta 2 when it's infinite, and by theta 1 being 0, theta 2 being pi, we get mu naught I over 2 pi r. That's the infinite wire. It comes from the finite wire, from the boundary condition setting up to infinite. All right, and then we did some math, and we said, hey, what if you have multiple wires? Just find the magnetic field due to each wire, and then combine them. When you combine them, be careful. These are vectors. Vectors do not just add. They only add if they are parallel to each other. If they're anti-parallel, they subtract. If they are at angles to each other, then you have to do trigonometry. And we walked through some examples of that. And that's what most of the problem set is hey, a bunch of different situations, a bunch of different types of wire combinations. Make sure you're good at doing that. All right, skip that one. And then the last thing we talked about was what if you had two straight wires? What's going to happen? They're going to experience a force on each other. Why? One makes a field, the other experiences a field. The same reason 2 point charges affect each other. One makes a field, the other experiences a field. These are great problems because they put everything together. They test if you can do all the pieces together. And so we just did a conceptual one of what direction will those forces be. And this does boil down to a simple rule that if you have two parallel wires, if the current's going in the same way, they attract. If the current's going in opposite directions, they repel. Why? You have to actually go through the Riemann rules to prove that. And we did that with the two wires going in the same direction. Why is the force to the left? So wire 1 makes a magnetic field into the page. So where wire 2 is, there's a magnetic field. Why is there a magnetic field? Because wire 1 makes a magnetic field. Which way is the field where wire 2 is located? We put our thumb in the direction of wire 1, we curl our fingers, and we find it makes a magnetic field into the page. We now have a current going up, we have a magnetic field going into the page. We use right-hand rule 1. Right-hand rule 1, fingers in the direction of current, so that they can swing towards the magnetic field, and we get a force to the left. You can repeat that exact same process backwards. Wire 2, well, I say backwards, you can do it the other direction. Wire 2 makes a magnetic field at wire 1, and that magnetic field will also be pointed out of the page. Why? Right-hand rule 2. Out of the page, that's the wrong symbol for out of the page. This is a dot. So this is the magnetic field due to 2. If I have a magnetic field pointed out of the page and I have a current going up, right-hand rule 1, fingers up. Now I can swing them out of the board, my thumb points to the right. You don't actually, when you find the force on one of these wires, the force on the other wire is equal and opposite. Newton's third law. For every force, there's an equal and opposite. Continues to hold true. All right, and this next slide is just kind of a putting the equations together. So this is not, well, okay, so this is just the force on a current carrying wire. And then you have to remember what makes that field. In the case of last, it depends. If it's an arc of wire, if it's a straight wire, whatever it might be is going to depend on what that field is. In the last case, it was an infinite straight wire. So we will very quickly solve this problem, and then we're going to keep moving. So I'm just going to kind of set it up, but I'm not going to solve it. I'm not going to put the numbers in for the sake of time. Wire 1 carries 30 amp upward. Great, there's wire 1. It carries 30 amp upward. Wire 2 carries 10 amps downwards and is 3 centimeters to the right of wire 1. So I got another wire that carries 10 amps downwards and is 3 centimeters, 0.03 meters to the right of that one. Wire 3 carries a current of 20 amp upwards and is 5 centimeters to the right of wire 2. So it's a little bit further. That's wire 3. That one's carrying a current of 20 amps, and that is 0.05 meters from wire 2. And the question is, what is the magnitude and direction of the force on a 25 centimeter length of wire 2? So it's asking for the force on wire 2, specifically a segment of wire 2 that is 25 centimeters in length. So F on 2 equals question mark. All right, so we got a couple options for how to solve this. They're both the same method, it just depends how you break it down. The two options are to find the fields where wire 2 is located and combine those fields together to get the net field. If we have the net field, we can get the net force. Or you can find the force that wire 2 experiences due to 3, the force that wire 2 experiences due to 1, and then do it that way. It ends up being the exact same mathematical process. So our question is, why does wire 2 experience a force? ILB sine theta. This is the equation for the force on a current carrying wire due to a magnetic field. We know the current in wire 2. We know the length of wire 2. We do not know the field it's in. How do we find the field it's in? We find the field due to wire 1. We find the field due to wire 3, and we combine them.
Wire 2 itself doesn't have a field.
Correct. That's a great question. Wire 2 does not make a field at itself. Wire 2 does not make a field at itself. Just like a point charge doesn't make a field at itself. Otherwise, it affects itself. So that's the equation for the force on 2. So now we just got to figure out B, and we're going to call this B net. Why are we going to call it B net? Because it's the magnetic field where it's located. The magnetic field on this line. What's causing that magnetic field? Wire 1 and wire. So B net is going to equal the field due to wire 1 plus the field due to wire 3. Now, I put plus signs here. We're going to have to actually determine how we're going to add these together. Currently, I'm just going to kind of put them as vectors. But because they're vectors, we need to find directions so that we can determine how we're going to add. Do I have to break them into components? Are they perpendicular to each other? Are they parallel, anti-parallel? Vector. Normal vector addition. So, go ahead and spend a few moments. What is the direction of the field due to wire 1, where wire 2 is located? What is the direction of the field due to wire 3, where wire 2 is located? I'm trying to find the field somewhere along this line due to each of these. Right now, just find the direction. So you're using right-hand rule 2 here. You're finding magnetic field. All right, so let's do wire 1. We put our thumb upwards. We then imagine the circle. And when we imagine the circle, we care about where wire 2 is located. What's the direction of the field where wire 2 is located? Into the page. Into the page due to wire 1. So wire 1 is making a field here that is into the page. Now, wire 3 is also pointed upwards. So we're going to do the same process. Point our thumb upwards. Make that circle. This time, my fingers are on the left side of it, because that's where the point is we care about. This is out of the page. Wire 2 or wire 3 is making the magnetic field out of the page. Just because both currents are up. This one we're on the right side of that wire, this one we're on the left side, so it flips things. So wire 2 or wire 3 is going to make a field that is going to be out of the page. Why? Right-hand rule. You got to practice this right-hand rule. There is no... If you're having challenges with right-hand rule, please find someone in person who can help you. That might be me, that might be someone in the help room, that might be up here. It's such a physical kind of thing, and there's so much visualization. It'd be great if I could draw a lot of pretty pictures of this in 3 dimensions. It's a pain in the butt to draw. This is something that I have found that in person is, it's so much easier. Like anyone that's online right now can't see me explaining any of this, and my words are not as good as they could be. All right.
The margin of error for like the right-hand rule for like, take for instance, I agree. Let's say I point my finger towards it, it's going in. The thumb's going up.
So this comes down to, can you visualize what's going on? There's kind of 2 ways. You can do the group. If you're doing that circle method I talked about, you need to be able to visualize this circle. That is the reality of when I'm talking about this magnetic field making a circle around it. You need to be able to visualize that circle. The other way doesn't require as much visualization, but you don't get a full picture, which is fine. If you do the other way, which is thumb up and flat, my palm points outwards. So it's fairly precise.
Right, I know, but I went like this and then we're going inwards.
So this one, if we just do this, wire 1 goes into the page, wire 2 goes out of the page. And that's just, it's pretty set on that. Yeah.
So the way you orient your hand is like based on like where the point is.
Yes, that's a great question. The way you orient your hand is the direction of current and where the point is that you're finding the field. Yes. All right. So, to clarify, when we then find the B net, I'm no longer going to write these as vectors because we're going to add them together. These are anti-parallel. I'm going to define out of the page as positive. I'm going to define into the page as negative because that's what most people would probably want to do. So, B3 is going to be positive. It's out of the page. B1 is going to be negative. So when I add these together, because they're anti-parallel, I can just add them as long as I assign the positives and negatives. You can flip the sign as long as you recognize, as long as you know what positive and negative mean. You got to make sure you're consistent. Yeah, so next we're just going to replace these with the equations. So we're going to remember that these are infinite wires. Rule of thumb, if I don't tell you whether a wire is infinite, if I don't tell you where the ends of the wire is, assume it's infinite. If I don't tell you where the ends of the wire are, assume it's infinite. It's a good rule. If it's going to be a finite wire, I will say one end of the wire is here. So this is an infinite wire. Infinite wire is mu naught I over 2 pi r. So to write this equation, we're going to have mu naught times I1 over 2 pi r1 plus mu naught I3 over 2 pi r3. You just plug in the numbers. What is r3? That is the distance from r2 to r3. R1 is the distance there, shown on the picture. Once you get this value, you just plug it into the force equation. The angle is going to be 90 degrees. This angle is the angle between L and B. In this problem, that is 90 degrees. L is the length of the wire that we're finding the force on. 25 centimeters. That's a great question. In fact, I'll go ahead and label that here. The length here is the length of the wire. Now, it is also common in these problems, instead of saying find the force on A and I give you the length of the wire, it's very common to say the force per unit length. Find the force per unit length. What does that mean? It just means you take this L and you divide it to the other side, and now the equation becomes F divided by L equals stuff. So that's a really common thing. If I said find the force per unit length, so I'll just kind of write this up here as a reference. This is force per unit length. Mathematically, that's what that sentence means. F divided by L is force per unit length. So that's a really common way of writing these problems. If you have an infinite wire, there is no length. It's infinite. So, all right. So that closes up kind of this section. So we're now going to segue into Ampere's law. Ampere's law is going to be something you've seen before in a different way, and at first you might groan about what it's going to look like, but then my hope is that it actually helps you in a lot of ways, and also the efforts that you've spent previously apply here. So let's see what I mean. Ampere's law. I just kind of jump into it. So Ampere's law says the integral of B dot dl equals mu naught I enclosed. Now, you have not seen this equation yet, but you have seen something that looks very similar. You all have seen Gauss's law. Gauss's law looks very similar. Gauss's law is E dot dA equals Q enclosed over epsilon naught. The way we're going to do Ampere's law is very similar to Gauss's law. But let's compare these two equations and we're going to see what's different. Obviously, instead of finding electric field, we're going to find magnetic field. So that's a change. Instead of integrating over an area, so Gauss's law, we drew an object and we integrated over its area. It depended on what our geometry was. If we had a sphere, we drew a sphere. If we had a plane, we drew a cylinder. If we had a line of charge, we drew a different cylinder. Fun fact, in this one, we're always drawing circles. We're always going to draw a circle. I'm not going to give you a problem where it's not a circle. So it's actually only one case for this, and we're going to apply that. Technically, there's two cases, but one's going to be used to derive. You don't actually need to know it. The other one, you do need to know how to set it up. So anyway, it's a DL instead of a DA. A length, non-area. The other thing is instead of Q enclosed, it's I enclosed. It's the same process that we're going to use. Except instead of enclosing a volume, we're going to enclose a cross-sectional area. Okay? So you're going to see what I mean as we do this. Gauss's law was in 3 dimensions. Ampere's law is going to be in 2 dimensions. Okay? It's kind of a simpler version of it, but it uses the exact same thought process. All right, so it's going to make the most sense by doing it. So, the first step is we need to choose our Ampere path. Just like we had to choose a Gaussian surface, instead of a Gaussian three-dimensional object we're just going to draw a path. Now, how do we choose that path? We choose that path such that this integral goes away. Either the dot product disappears, either the dot product is 0, or the magnetic field is a constant. Just like we chose Gauss's law. We chose Gauss's law to make the electric field a constant or to make the dot product disappear. So, straight wire. What is the path I'm going to choose around this object such that everywhere in this hypothetical path, the magnetic field is a constant? So let me draw what I mean by this. I'm going to draw each answer, and then we're going to see, and then you're going to answer which one makes sense. So I want to find the magnetic field at some point. I need to draw some kind of loop around it, some kind of path. Am I going to draw a circular path around it? Am I going to draw a square path around it? So it's kind of a pain to do this, but whatever. There's my square path. Am I going to draw a triangle path around it? Or am I going to draw a figure 8 around it? The key is, which of these shapes that I just drew, which shape has the magnetic field the same everywhere around it? So which path, everywhere in that dotted line, I want the magnetic field to be a constant. What path are you going to choose? Circle, square, triangle, or figure 8? All right, 20 more seconds. Yeah. 2 weeks from this Thursday. All right, in 5, 4, 3, 2, 1. So I'm very happy to see that this is looking pretty good. What is the path that a magnetic field is constant everywhere around it? It is a circle. If I draw a circle around this thing, the magnetic field everywhere on this path has the same value. It's a constant. Not only is it constant, this is the direction of the field at every point along this path. So when I look at this integral, b dot dl, remember this integral is actually b times dl times the cosine theta. It's a dot product. It's the angle between b and dl. Oh, which way does dl point? It's the direction of my path. It is the same exact direction as b everywhere on this. So b is a constant. The angle is a constant. So what's the benefit of that? I can pull b out of this integral. What is the integral of dl? It's just L. What is L? Is the length of this circle. What is the length? I.e. the circumference of a circle. 2 pi r. So this is what we're going to do for every single one of these Ampere's law. The only problem I'm going to give you with this are wires. Now, we might get inside the wire and find the magnetic field inside a wire, because wires actually have thicknesses to them. But yeah, this is what we needed to know. This is the left side of the integral, always. For every problem I'm going to give you, it's just going to be this b times 2 pi r. For this reason that you all just identified. So look at that. All right, so how do we do Ampere's law? Same way we do Gauss's law. Kind of sort of with some modifications. Draw a dotted circle. It's always going to be a dotted circle. Draw a dotted circle around your wire that intersects the point you want to find the field at. Solve for B dot dl. It always ends up being B times 2 pi r because it's always a circle. Where r is the distance to the point that you care about. It's the radius of that circle you drew. Now we're going to solve for I enclosed. How do you find I enclosed? The same way we found charge enclosed. But instead of a volume, it's going to be an area. We're going to find how much charge is enclosed by our circle. If all the charge is enclosed, just put the charge. If all the current is enclosed, just put the current. If a partial amount is enclosed, you will need to find the current density. It's the same as charge, it's charge over area. It's charge over area. It's fine. We're all done this a bunch. You just did charge over volume a bunch last time. If multiple wires are enclosed, find the enclosed current for every single wire, and then add them all up. And then set two sides equal to each other and solve for B. Don't forget to do that.
What if there's no current?
There's no current, then yeah, and that's a good question. Why would there be no current? If I have two current carrying wires and they're in opposite directions, they'll cancel each other out. Yep. So in this case, there is such thing as positive current and negative current. Positive current is one direction, negative current is the other direction. Positive and negative here, when we talk about current, is defined on the direction it's going. That is an important thing to consider. All right. So we're going to do Ampere's law to find the magnetic field due to an infinite wire. We're going to actually derive it. In fact, I'm going to change all this purely to variables. I'm not going to put numbers in here. Use Ampere's law to find the magnetic field r away, a distance r away from a wire with a current equal to I. Previously, to derive the equation for an infinite wire, we had to do an integration, and it was unpleasant. This is going to be so easy.
Does Ampere's law work for both finite and infinite wires, or like?
It works for... You do need an infinite wire. That's a good question. The wire has to be infinite for you to use Ampere's law, just like we had a similar problem with Gauss's law. Yep, due to symmetry requirements. All right, so let's go ahead and do this. Look, I already drew the dotted circle for you all. So that would be normally the first step. Find some, you know what? Let's just delete this picture. Let's just draw this. So here's my current carrying wire. We're just going to say it's into the page. It doesn't really specify here. We don't really care. It just says let's say find the magnitude. Find the magnitude. That way we don't have to care about direction. Magnitude. Great. So we want to find the magnetic field some distance p away from it. So we draw our wire. We draw a circle around it. Ideally, you draw your circle better than me. This is okay, but it's not very symmetric. All right. Then we write Ampere's law. B dot dl equals mu naught I enclosed. We do one side at a time. The left side, it's a circle. Talked about that. So this turns into B times 2 pi r. Because it's a circle, the length around a circle is that. Great. The right side is mu naught. What's my current enclosed? It's just I. It's literally all of it. You can tell from the picture it's all of it. Rearrange this equation. B equals mu naught I over 2 pi r. We derive the infinite wire in two lines. It's nice. The alternative is doing an integral with trig sub. Yeah, it took way longer. It took 2 slides or so for us to do. So you can see the power of symmetry, and Ampere's law is very useful for helping determine problems that would otherwise be disgusting. And this is one example of it. We're now going to look at some other examples. All right, I'll leave that for a couple more seconds, just for anyone that wants it. But this is the simplest case, i.e. we have all the current enclosed. You just put what that is.
But isn't it in terms of data?
That's for an arc. That's for a finite wire.
So 2 pi r is still in length?
Yep, r here is the distance to the point. So this is the equation for the magnetic field, a distance r away from an infinite wire.
Oh, right.
All right. So I told you all this before. The direction of current matters. So find I enclosed in the following picture. I have 3 amps going kind of over here. I got 2 amps going up. I got 4 amps going down. And they drew some random circle. That's the ampere loop. You are caring about the I enclosed by this orange loop. What is the I enclosed by this orange loop? We're going to define, we're not worried about the direction. Okay, so none of these answers are positive or negative. Don't worry about that. Find the magnitude of the current. If we want, we'll define down as positive. Oh, no, it's way easier than that. No, this is a quick problem that you can do in about 10 seconds. Oh, that's just one going through this one. Yeah. This loop, these wires are connected. This loop was just kind of drawn opaque to help you see that it's intersecting. Direction matters. There's a hidden plan that says that. All right, 20 seconds. All right, in 5, 4, 3, 2, 1. All right, so again, maybe I should have put it doesn't really matter. This one of them's going up, one of them's going down. One of them goes through the loop this way, one of them goes through the other way. So you subtract the 2. Direction matters. Direction matters. So we'll just do 4 minus 2 equals 2. Yay. What's important here? Why does this matter? Say I had a current carrying wire that was going into the page, and surrounding it was a current carrying wire going out of the page. And you're like, why would this possibly exist? What possible scenario would you have current going in 2 directions? Every single wire that possibly exists. Every single wire has current flowing in and out. You need a closed loop. When you plug in something, you need a current that goes in. You need a current that goes out. Every single wire that you will ever plug in has current going in and out. Then current's not going to flow. You need an out, a closed loop. One great example of this is called a coaxial cable. A coaxial cable has a thin wire in the middle and an outer jacket around it. Current goes one way to the middle, the other way on the outside. What is the magnetic field outside of that wire? 0, assuming the currents are equal to each other, which they generally are.
What about like cables,
Internet cables, same idea again, unless it's an optic cable, in that case it's using light. All right, so this is important for you all to know because most wires carry current in multiple directions. All right, this one, I am very proud of this problem because once we draw a picture, I really hope you all recognize this picture looks similar. All right, a thin wire carries a current of 3I. Let's say, I didn't give directions here, I should have. Let's say it's into the page. Or let's say okay, I'll clarify that later. A thin wire carries a current of 3I and is at the center of a thicker wire with radius R that carries a current of I. What is the magnetic field at some point R less than capital R? Let's draw a picture of this and let's assume, it should have specified, both currents are in the same direction. I need to specify that. Generally, if it's not specified, you can assume. Let's draw a picture of this, and I really hope when we draw this picture, it looks familiar to you all. So we got some thick wire with radius R, big R. Somewhere inside of it is a really tiny thin wire. So this one carries a current of I. This tiny one inside it carries a current of 3I. You're like, wait, what? Does this look familiar? Shouldn't it look familiar? On the test was a Gauss's law problem with a sphere with radius r. And at the center of the sphere was a point charge with charge 3q. Or a 2q if you're depending on what version you have. We're going to use the same ideas, but slightly modified because it's 2D versus 3D. This is a 2D slice of this wire. This wire is coming out of the page. When we do Ampere's law, it's a 2D slice of the wire. Okay? But we're going to do the same process. I want to find the magnetic field at some point P that is inside the wire, a distance r away. What is our first step? Draw the dotted line. So I'm going to move some things around because it's going to kind of conflict with things. Circle wire, circle path.
Does it matter how big you make the circle?
That's a great question. Does it matter how big you make the circle? No, as long as it has a radius of little r. That little r, the only requirement for that is it's less than big R. So the equation we're going to get will be true anywhere inside this thing as long as I'm in between the middle and the outside. The equation we work, this is why variables are fantastic. Once you put in numbers, you get a specific answer in a specific spot. The solution we're going to get will be true anywhere inside it for any r less than capital R. So that's the benefit of equations. So we write B dot dl equals mu naught I enclosed. We do the left side first because it's on the left, and that's how people read. So we'll just pick that. Doesn't really matter. Okay, it's a circle with 2 pi r. Well, that was easy. Left side easy. In the case of the problem that you all did on the test, it was a sphere. So it was the area of the sphere. Gauss's law uses area, not length. So it's 4/3 pi r cubed. All right, the right side. We need to find I enclosed. I have 2 current carrying wires. So what is my I enclosed? It is the current enclosed for the tiny wire. It is the current enclosed for the big wire. 2 wires. Find the current enclosed for each of them and add them together. The current enclosed will be the current due to both wires added together. So we could call this like I1 enclosed plus I2 enclosed. It's 2 wires. We'll call this one in the middle 1. We'll call this one on the outside 2. Now, I1 is very easy. How much current is enclosed for this wire here? All of it. This tiny little wire is completely inside my circle. So that is easy. That is 3I. I2 enclosed, we do not have all of it. We do not have none of it. We have some of it. How do we find it? Remember, when we have some of it, find the current density and multiply by the current area enclosed. So let's just kind of write that out. So to find this current enclosed, and I'm going to steal the space up here. Remember this is true. So it's a surface. It's a 2D distribution of current. The current is distributed over an area. We will assume uniformly distributed. That is going to equal the total current divided by the total area. That will equal the current enclosed over the area enclosed, because it's the same everywhere. So if I have all of it, I take all the current divided by all the area, gives me the exact same thing as sum of it divided by sum of it. All right, using this equation, we don't actually care about the current density. You can solve for it if you want, but we could just use this left side. Why can we use that left side? Let's go ahead and try it. I total over area total equals I enclosed over area enclosed. Solve for I enclosed. It's going to equal I total over area total times area enclosed. Now we just put what those are. What is the total current in my big fat wire? I. Just I. What is the area total? Pi capital R squared. Big R for big area. What is the area enclosed? Pi times little r squared. It's a ratio of areas. Pi's cancel. So what is the solution to this? I enclosed equals I times little r squared over capital R squared. I's canceled, I is I, little r is on top. Great. Now let's put those in. Mu naught times 3I plus I times r squared over big R squared. Yeah.
How are we able to do that ratio again? That's just kind of...
Yeah, because that's a good question. We're able to do this ratio at the top right because the chart, we're going to assume the current is distributed uniformly through the wire. Just like mass is, it's like a density, like mass density. And so the example I give people, if I found the density of this piece of paper, if I ripped off a piece of it, I found the density of this piece, this tiny piece, they have the same exact density. Yeah. So that's a great question. And that applies to anything that has a uniform. There's all sorts of different, there's mass density, charge density, current density. There's anything that have a distribution of over space, there's a density version of it. Yeah. All right. This is basically it at this point. You just do the algebra. The most common mistake that people made on the exam was not realizing there was two objects, and I needed to find on the exam it was two different charges, and just add them together like this. This is the same process, but with currents. Same idea. Two objects, find the current due to each. So you rearrange this. I'm going to factor out the I because they both have it. Divide the 2 pi r over, and I get 3 plus little r squared over capital R squared. That's good enough. Yeah.
You can't cancel one of the little r's, right?
The question is, can I cancel one of the little r's? Only if you took this r to both terms, in which case the 3 would have an r underneath it as well. So it doesn't really make it any prettier. Yeah, this is about as simplified as we can write it. All right. That's it. And this looks very similar to the solution from test 1, except it's cubed because it's volume instead of area. And it's epsilon naught instead of mu naught. Epsilon naught's on the bottom. Cubed instead of I. Great. There you go. Nice little review of things. Okay, now I got to teach you all about a solenoid. So we learned how to do an infinite wire. That's kind of the one that you need to be able to do this type of problem fully worked out. It is so easy for me to make many versions of this. It's so easy for me to put a wire inside of a wire inside of a wire. It sounds silly, but you can do it. It's not too hard to make a problem like that. The solenoid, we're going to derive, and we're just going to end up with an expression. You do not need to know how to do the derivation, but this is to help us understand where the solution is going to come from. We're going to get the magnetic field due to a solenoid. What's a solenoid? We're going to discover what a solenoid is. So, which way does the magnetic field go to point P, which is the equidistance for a wire going out of the page and a wire going into the page? The wire going out of the page is on top, wire going into the page is on bottom. Is the magnetic field at point P, to the left, to the right, up, out of the page? Give you a whole minute. All right, I'll give you all a bit more time. It seems like we're still needing a bit more time to do this. Find the magnetic field to each wire, draw them, then add or subtract each beam. All right, 15 more seconds. Alright, in 5, 4, 3, 2, 1. Alright, so wire 1's going out of the page. So we put our thumb out of the page. We make that circle, and our circle at the bottom points to the right. So the magnetic field with the top wire points to the right. Do the same thing for the bottom wire, but now your thumb points into the page. Thumb points into the page. Make that circle at the top point. The magnetic field still points to the right. I got two fields to the right, so what are they going to do? Add together. It's going to point to the right. Now, all I need to now convince you all of, so this is just good practice, this is what a loop of wire will look like. You're like, what do you mean it's a loop of wire? Imagine a loop of wire that comes out of the top, circles back around into the bottom. This is the magnetic field due to a loop of wire that's, intersecting the board. To kind of draw this really ugly, imagine that there was like an axis like this, and that this was a loop going like this. If you all did the right-hand rule, the shortcut way, loop your fingers in the direction of this current, and it still gets you the same exact answer. So this is actually what a loop of wire looks like from the side.
Can you show them the right-hand rule again?
Yeah, so real quick, current goes out, points to the right. Here, current goes in, points to the right. So, this is a loop of wire. I tricked you all into solving the magnetic field due to a loop of wire that goes into the page. Now, what if I had a whole bunch of loops of wire? So many! Take a guess, based on what we just did. Do I actually want you to solve this for every single loop? Not necessarily. If you have the time, go for it. But take a guess. If one loop of wire pointed to the right, which way do you think a bunch of loop of wires is going to point? And I purposely picked this point a little bit above center to make a point. But you don't actually need to worry about it. That's my hint to you all. Doesn't actually matter, and it's a little bit closer. Yeah. So what's interesting here is it affects the magnitude. It affects the direction for like the one to left and right of it, but it ends up not mattering. And I'll show you why as I draw some arrows. Oh, and to clarify, there's an infinite number of loops here. I can't draw an infinite number, but imagine that there's an infinite number of X's on the bottom and an infinite number of dots on the top. Infinite numbers of things making sense. All right, give y'all 10 more seconds. All right, in 5, 4, 3, 2, 1. Okay, so the one directly above it and the one directly kind of here, not a hard argument to make that those point to the right. Now, if you consider this one that's slightly here, what's going to happen is it's going to be a circle. Now, that circle is going to be fairly horizontal at that point. So if I just drew a circle around this dot, we're kind of fairly horizontal. Whereas if you drew a picture around this one way down here, we actually end up with a little bit more, well, it's actually even more horizontal. So I need to clarify this. You do not need to necessarily know this too much. This one's stronger, this one's weaker. Anyway, due to symmetry, I'm just going to hand wave this a little bit. The logic I used was correct. For every wire up here, the magnetic field is going to kind of point up to the right. For every wire on the bottom, it's going to point down to the right. What's going to end up happening with all our ups and downs? They all end up canceling. And it ends up not mattering about distance, and the reason it doesn't matter about distance is because the ones up here point a little bit more up, so the components are a little bit less, and yada, yada, yada. I'm not going to spend too much time on it. All I need to convince you all of, the magnetic field everywhere inside this points to the right with the same amount, regardless of where you're in it, because it's infinitely long.
Would it be a different direction if, let's say, you had 6 on the top plate, out of the page,
Yeah, that's a good question. If I have more on top and less on bottom, yeah. The key here though is this is a loop, and for every loop, the top goes out and then it has to go back in on the bottom, so we always get an equal number. Yeah, the key here is these are not actually a bunch of wires going out of the page on top and a bunch of wires going, I mean they are, but it's actually loops, and the loops always come back around, so you get an equal number. Then it'd be the other direction. That's a good point. All right, so this infinite amount of loops of wire next to each other is a solenoid. It kind of looks like a spring or a slinky or anything like this that wraps. What is very important is that this wire has an insulating material around it. So these are not just bare metal wires. Why is that important? If it was a bare metal wire, why should it go in a circle? It's not going to go in a circle unless it has to. If this is all metal, it's just going to go straight up and it's not very exciting for us. So to make a solenoid, you need an insulating wire. You need an insulating wire such that these loops can't short. If they shorted, if this was a hunk of metal, why should they go in a circle? Current takes the shortest path it can. So we're going to force it to take that long path by making an insulator around it. This is an engineering thing. Your wires need to be covered. Now, obviously if it's covered with rubber, that's insulated. Like you all see wires covered with rubber. Just fun fact for you all, there is wires that are insulating on the outside, but it doesn't look like it. There is these copper wires that have like this orange tinge on the outside. I don't think it's bare copper. It's not. It's a very thin painted layer of insulation on it. So you can make these wires really thin, not by coating them with rubber, but by coating them with like this paint. We're going to call it paint. This insulating thin layer. You don't need that much insulation. And you might not be able to tell that, and when you plug stuff in, you're like, why aren't I getting any connection? You actually have to scrape off that if you want to actually connect it to something. So that's just, fun fact for you. All right, but the important thing is this loop looks like the problem that we just did. If you take a slice of it, just to kind of zoom in here, look, a bunch of dots and X's. If you take a slice of it, this coil looks like a bunch of infinite wires. If y'all can do a bunch of infinite wires, great. Now, what's important is this thing has a certain number of loops. We assume it's infinite, but in reality it's not, but we kind of just ignore those two things yet. N is the number of loops, how many times it spins around. L is the length of the solenoid, it's how long it is, to draw that on this picture. So this is L, the length of the solenoid. N is how many loops. It's very common for us to report this as turns per length. Turns per meter. That's pretty normal. To kind of condense those into one term. All right. Why are we talking about these? These are called solenoids. Solenoids are present in almost every single circuit you all mess with. This is the last circuit element I'm teaching you in the class. We have resistors, we have capacitors, we have like batteries, / voltage sources, and we have solenoids. What does a solenoid look in a circuit? Literally like this. If you all look in any electrical circuit, a solenoid looks exactly like that, specifically a coil of wire. So, let me see, solenoid, these are often called inductors. We're going to learn about inductors.
It's not a little thing that shoots up?
No, so I'm trying to find, all right. So here's some examples on circuitry. This one on the right is kind of exaggerated, make it steady across. That's an example of a solenoid. They often are just kind of open. You often can see the turns of the wire on them. Why? I think just space-wise, it's inconvenient to cover them, and it's not necessary. But this is really common to see these things on circuits, these loops of coils. Why? We'll learn why next week. But for now, I'm just telling you why we care about this, just like when I taught you about parallel plates. Infinite parallel plates. Why do we do that? Because of capacitors. Why are we doing solenoids? Because these are inductors. In every single electrical circuit, we generally have most of them have an inductor in them. And there's benefits to them. We'll talk about why next week. All right. We need to find the magnetic field in the solenoid, just like we need to find the electric field in a capacitor in an infinite plane. How are we going to do that? We're going to do some hand-wavy things here. They're not hand-wavy, but they're going to sound a little silly. We're going to use Ampere's law. You do not need to know how to do Ampere's law for a solenoid, but I'm just going to show you it. It's pretty quick. It's pretty easy. The path we're going to choose is a square. Why are we, again, you do not need to know this. This is not something I'm going to test you on. We're going to choose a square. Why do we choose a square? If I want to find the magnetic field at some point P, everywhere along this bottom path, B is a constant. Everywhere along this dotted path, B is a constant. So that's helpful for us. Why? Remember, the rule. We want B dot dl to either equal B times L, or we want the integral of B dot dl to equal 0. We're integrating over this path. We got 1, 2, 3, 4 sections of that path. So, looking at one section at a time. On the bottom, this is very nice. On the bottom, on path 1, integral of B dot dl ends up being just B. And in fact, I'm going to write this. I don't want to keep writing this a million times. Remember you all that the integral of a dot product is dl times cosine theta. So I'm actually just going to write that from now on, so I don't have to keep writing it twice. B times dl times cosine theta. On the bottom path, B is a constant. It comes out. Cosine theta is 0. Why? B points to the left. dl points to the left. The angle between them is 0. So you get the integral of dl. That equals B times L. Easy. Great, that's the bottom side. Let's now look at path 2. On path 2, which way does the field point? To the left. Which way does dl point? Up. On path 2, what does that integral become? B, dl, cosine theta. What's the angle between these? 90. What is cosine of 90? 0. Boom. That side's 0. By the same logic, side 4 is also 0. Now, I'm going to do something for side 3 that is going to sound very silly, but there's no rules against it. I'm allowed to do this. We're going to take side 3 and move it infinitely far away. It sounds silly, but we're going to see why. We're allowed to do this. There is no rules with these loops. We can pick whatever loop we want. We're going to take this side and move it infinitely far away. We're allowed. Why are we going to do that? Let's see what's going to happen when we do this integral. Now, something I didn't note is that outside this, we're going to assume the field points the other way. It's going to make a circle. So on the inside, it points to the left. On the outside, it points to the right. You know, it loops back around. Okay, great. So why am I doing this? I got to write the integral real quick, and then it's going to be really simple to show you all. What is the magnetic field infinitely far away from the solenoid? 0. So it's 0. This sounds stupid, but if it works, it works. I've not broken any rules. If I make side 3 infinitely far away, what is the magnetic field infinitely far away? It's not a stretch to say it's 0 if you're infinitely far away from this thing. No, I don't think so. Oh, well. For the same reason as 2, this side is going to be 0. So what have we done here? We have turned this path integral into just B times L, where L is the length of the body. You do not need to know how to do this, but it's good for you to kind of see it didn't come out of nowhere. All right, that's the left side. Yeah. Yeah, so we've only done the left side currently. We're going to now do the right side. So yeah, so to sum up this, B dot dl ends up just being B times L. Now we're going to do the right side, because we can't solve this without the right side. So I'm going to take this, steal it over here. I still need my picture. I'm going to steal that in just a second. This ends up being really simple, but just choosing that path is really the only complicated parts. All right. So this is going to see the current enclosed is actually going to be quite nice. So we're doing B dot dl equals mu naught I enclosed. Now we're going to do the right side. What is the current enclosed? It's really simple. Count the x's. It sounds stupid. How much each of these wires, remember this is the cross section of this. Each of these x's is one of those loops. So how much current is enclosed? I plus I plus I plus I. Sounds stupid, but that is the current enclosed. It's how many wires do I have enclosed? How are we going to express this? I'm not going to do addition because that's going to be a bit of a pain. What I'm going to do is say how many loops are enclosed. Remember, each of these is a loop. loop, 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 loop. I know this looks like a solid bar. It's not a great picture. It's a bunch of dots. How many dots are enclosed? How many loops are enclosed? So we replace that with N. N is the number of loops enclosed. If I enclose 10 loops, I'm going to get 10 dots. 10 times I. If I enclose 5 loops, 5 dots. Great, set these two equal to each other. B times L equals mu naught IN. Solve for B. Mu naught I times N over L. That's the equation for a solenoid. That's it. Now, there is something very important about this. Again, to keep drawing connections to a capacitor. Did we care where we were inside of this thing? At any point, do you all see any distance dependence for where I'm at inside the solenoid? Any R? Any D? No. The magnetic field is a constant inside of a solenoid, just like the electric field is a constant inside a capacitor. That's why they're used. So this is the same derivation, and I'm going to make this explicit, so I'll make this a little bit, I'll zoom back in. This is the equation we just derived. This is the equation for the magnetic field in a solenoid. This is on a formula sheet. Mu naught I N over L. This is capital N. You can replace capital N with capital N, like lowercase n is capital N over L. N is N over L. All right? Something very important. I'm going to put this. The magnetic field is a constant everywhere inside the solenoid. And I'll even remind you all of the thing I did last time. Just like the electric field is a constant everywhere inside a capacitor. This is why we use them in circuits. This is why a capacitor is used in a circuit. This is why a solenoid is used in a circuit. It's some device where the capacitor, electric field is the same everywhere. Solenoid, magnetic field is the same everywhere. And we always assume these solenoids are infinitely long when obviously they're not. Yeah.
So if you wanted to make a stronger magnetic field, you would just add more.
That's exactly right. That's a great question. The question was, do we make a stronger magnetic field? Do you just add more loops? Yeah. Specifically, more loops in the same length. So you don't want to make your solenoid longer. If you do, then you make the L bigger. Correct. If you all look at these solenoids, if you all want to make a strong magnetic field, you take a bunch of loops of wire and you stack them on top of each other. And that is every single circuit. These solenoids are everywhere. Electric motors, it's a bunch of solenoids. It's a bunch of wires. How do you make it really strong? We're talking thousands of loops of wire here. This is not or hundreds to thousands of loops. And these really thin wires, now there's limitations. You need a thick enough wire that the current can actually flow through it without getting the wire too hot. Generally not too big of a problem though. But generally you want a bunch of loops of wire.
What's the difference of using thin loops of wire compared to just one thick?
We kind of treat, so the reality is we do kind of treat these, even when it's like really tight packed and it's clearly not infinite, we just pretend like it is. It's very hand wavy, but yeah. We tend to just jam these things in there. All right. It tends to not matter too much, honestly. For certain applications, we don't care too much if the magnetic field is super uniform, as long as it's the same in other devices. All right. Sure. Try it out. What's the magnetic field inside a solenoid with 200 turns per meter and a current of 3 amps? Notice I did not tell you where we are inside the solenoid. Why? It doesn't matter. So if I really wanted to make sure you're paying attention, maybe I'd ask a question like on the last test where I said, hey, last test I said I go 2 times farther in a capacitor. What happens to the electric field? Nothing. What if I made a solenoid with twice the radius? What happens? Nothing. Nothing changes. We don't care about the radius of the solenoid. Alright, and this will give you all like 8 minutes to start Faraday's law, but that's fine. It'll be still work. Yeah, I got 2 different units here. Make sure you know what the unit is for magnetic field. These are both units for magnetic field, but which one actually does our equations output? Do our equations output Tesla or do they output Gauss? Mu naught is 4 pi times 10 to the minus 7. All right, give y'all 30 more seconds. Look, I'll even give you the equation. Since it did just show up, we haven't used it before. All right, 10 more seconds. In 5, 4, 3, 2, 1. All right, so you plug in the numbers and you get 7.54 times 10 to the minus 4, and the unit's Tesla. There you go. Why is the unit Tesla? Because that's the base unit that we use. That's the unit. Huh? Oh, it's random. I don't know. There's no rhyme or reason to this. All right. Now, I do have a few minutes to just remind you all, what did we learn in this PowerPoint? To summarize it, we learned the magnetic field due to 3 different types of wires. An arc of wire, a straight wire, and a solenoid. Those are the 3 equations for magnetic field that are going to pop up on the formula sheet. B equals, it'll be 3 different ones. We learned Ampere's law, which is kind of like Gauss's law. Now, we're going to go ahead and start the next PowerPoint just very briefly. It'll give us a nice... We're just a little tight on time, so I'm going to use all the time I have available to me to make sure that I'm covering what I want you all to know, what I think your future teachers' classes need you to know. Obviously, we're not going to get very far in this today. We got 10 minutes. Faraday's law. All right. We have learned that in a magnetic field, a current carrying wire experiences a force. And we learned this is how motors work. We learned that motors work by you have a magnetic field, you have a current carrying wire, it pushes it. You convert electricity into motion. What if you want to do the opposite? What if you want to convert motion into electricity? That is Faraday's law. That is what this whole PowerPoint is on. We know how to go from magnetic fields to force to make motion. This is going to be from motion to electricity. This is going to be the foundation for how every single generator works. Every coal power plant, nuclear power plant, generator, in your backyard if you own one, solar or wind turbines. Almost every single source of power generation is going to be explained by Faraday's law. The only one that will not be explained is solar. Solar does not operate based on moving parts. But every single other form of electrical generation I know of, other than batteries as well, involves making something spin. Every single generator makes something spin. A coal power plant and a nuclear power plant operate the exact same way at the end. They make water get hot. Water turns into steam. Steam spins a turbine. Same with a wind. It's making something spin. Same with a hydroelectric dam. It's making something spin. Same with a generator you buy from Home Depot. It's making something spin. Same as the alternator in your car. It's making something spin. So this one PowerPoint that we're going to cover in 2 weeks will help you understand every single source of power generation out there.
It's gonna take 2 weeks.
No, 1 week, 1 week. All right. Now, to be able to understand this, we need to remember magnetic fields. We need to remember flux. We've covered electric flux. Magnetic flux is going to be the same thing, but with a B instead of an E. We need to remember area vectors, which way those point. We need to remember forces due to magnetic fields and voltage and, things that hopefully you're familiar with. All right, so we're going to learn what magnetic flux is. That's going to be really easy. We're going to identify what EMF is, which is going to sound fancy, but it's another word for voltage. Everywhere we see EMF in this PowerPoint, you can pretend like it's voltage, and that'll get you perfectly fine. Just another phrase for it. We're going to learn how to calculate this voltage due to a changing field, the direction of the current, and by the end, why do we care? Already tried to say this generators, transformers. We're not, unfortunately, going to be able to get to those too much, but it'll be what it is. It's fine. All right. So we're going to do these last 2 questions. We got the time for them. See if you all remember flux. If I have an electric field pointed upwards with a magnitude of 8 newtons per coulomb, what is the electric flux through a plane, which is 2 meters by 3 meters? The plane is flat on the x, y plane, i.e. its vector points up in the direction of z. What is the flux? You can hopefully do this math in your head. But feel free to use a calculator if it works. All right, give you all 20 more seconds. I want to be able to cram the last clicker question in. There's one more after this. All right, in 5, 4, 3, 2, 1. All right, the equation for electric flux. Technically, it was an integral. Now, if it's a constant, this turns into this. If it's a constant, which in this case it is, but it's not always going to be. Well, I think you are actually to be spared that. Cosine theta, E is the field, A is the area, theta is the angle between the two. This problem is really easy. It's 8 times 3 times 2, and the angle here is 0. Why is it 0? Because they're lined with each other. Great. We got enough time, I think. All right, find the magnetic flux. Same system. 8 Tesla field, which is a ridiculously large number, but I want to keep the numbers the same. 8 Tesla. The field is still 2 by 3, but now it's at an angle. Fun fact, if this had been electric, it would have been the exact same process. That's what I'm trying to convince you all. If I see if y'all can do this angle nonsense. The only thing that changed in this problem was E turned to B, and now there's an angle. So you just need to find that angle in that equation. It's the exact same equation with a B instead of an E. All right, give you all about 30 more seconds. I think that'll work out. All right, in 5, 4, 3, 2, 1. All right, this is making sure you remember that's the area vector. This area vector is going to be 60 degrees. Why is it 60 degrees? Because of the picture. You got to be careful with those angles. All right, y'all, we'll continue this next time. See y'all then.